I'm Neil Mitchell, and today I'm going to be talking about writing interpreters. In particular, cheaply writing interpreters that give reasonable performance. There'll be some code snippets on the slides, but if you want to see the full code, you can see it at the GitHub repo that's on the slide now. So, if we want to evaluate a language, how do we proceed? Well, for languages like C and Rust, we'll often compile them, producing static assembly code in advance that we then run at runtime. For more dynamic languages, like JavaScript or Python, we'll often interpret them. And within the concept of interpretation, there tend to be two broad approaches. For languages like JavaScript, which are executed very heavily, there's a lot of expensive operations performed in order to get the absolute maximum runtime performance. And techniques that are used here are things like just-in-time compilation and dynamic generation of assembly code. Then there are languages that are still popular, but less common. And these are languages like Python. And if you look at the Python interpreter, CPython, it doesn't have any assembly code generation. It just runs through your code using a bytecode interpretation approach. No assembly code, cross-architecture, much less cost to write, and a bit slower. And that's the kind of interpreters we're going to be looking at in this talk. So in this talk, we're going to focus on cheap interpreters. And the definition of cheap I'm using is that they have a low cost of development and a low cost of ongoing maintenance. And looking at cheap interpreters, I think that's probably pretty synonymous with not having any runtime assembly generation. As soon as you have runtime assembly generation, you have to have people who have expertise in both the host language and assembly code. You need to port it to different architectures as they come out, for example, the M1. And you need to have a way to trampoline back from the assembly code into your host runtime system. So the fact that we're not generating assembly code makes it a cheaper option, but we're still going to have to read some assembly code because we still want these interpreters to be as fast as possible. This is not the best way of writing interpreters. You absolutely can do better by generating assembly code. For example, the V8 runtime for JavaScript or the Lua runtime both do better, but at greater cost. As an example of where this technique might reasonably apply, consider the language Starlark, which is roughly deterministic Python. That's used by the build systems Buck and Bazel to describe the build graph that the build system then executes. It's more about writing interpreter configuration. How would we write an interpreter for this language in Rust with reasonable cost? So there are a bunch of approaches we can try. We can evaluate the abstract syntax tree, we can generate bytecode, and there are other approaches. And we're going to go through these in this talk. But before we do, let's look at a benchmark. In order to fairly compare the approaches, it's important we can compare them based on the real speed they give. So let's use this as our running example and benchmark throughout the rest of the talk. We have a loop that loops through 1,000 times, manipulating x. And we just do additions of x and constants to each other. And then at the end, we return x. We've deliberately only used plus so that we've maximized the interpretation overhead. If you had more expensive operations as the atomic units, then the interpretation overhead would be much lower. So the numbers you're seeing in this talk are very much the worst case. And in reality, some of the operations that are being performed in real systems might mean that the interpretation overhead is completely dwarfed by those operations. So let's implement the simplest thing we can. Just walk over the abstract syntax tree and evaluate it, doing what it says. Here we're defining a function in Rust called f that takes as its arguments x, the expression, the abstract syntax tree, and v of type v, which is just the variable storage. So this is just where we're putting the I and the x. And it returns an I64, which is Rust speak for int. All we do is we match on the expression. If it's a literal, we return the value immediately. If it's a variable, we look it up in v's. The interesting one is add. If it's add x and y, we evaluate x and add it to the result of evaluating y. Very simple, very direct. So this simplicity has a performance penalty. But would you like to guess what the performance penalty is? Before you do, I should say, we've done all the obvious things. We're using unchecked array accesses, which isn't the default in Rust. We've converted the variables I and x from being strings to being integers, 0 and 1. There's no allocation happening in this code, and we've optimized the Rust code with -o. And for the rest of the talk, we can just assume those things are done throughout. What do you think the performance penalty is? Well, the answer is 570 times. And if you think about that in a more kind of concrete way, that means that an operation that did take 2.5 minutes would now take a full day, a full 24 hours. For something like a build system, it's okay to wait 2.5 minutes. Not ideal, but it's okay. Whereas waiting 1 day makes the build system pretty useless. But was that a fair comparison? Not really. So the Rust compiler, it saw our manipulations on x in the inner loop, and it rewrote them to x equals x plus 13. So it cheated. It didn't do as many additions, it didn't do as many assignments, it didn't do the interesting meat of the problem that we were hoping it would. To ensure that it doesn't cheat, we can change the plus for a function with a no-inline annotation on it that does the addition. And this makes it slightly more representative of real work, where in practice, for many operations, you're going to have to actually run some meaningful code. So now we've done the plus properly, it's only 6.4 times slower. So that's the difference between making and drinking a glass of water and making and drinking a cup of coffee. Tolerable, but we'd like to do better. So I've now added orange lozenges to the talk, and as we explore new approaches, we'll keep adding to them to this sidebar. So we can see the Rust, the native execution of our benchmark, is at the bottom, and then 6.5 times higher up is the AST. So, what does the AST walking do? It matches on AST nodes, and then performs operations. Could we make it match on the AST nodes only once? Well, yes. We can go through and generate closures. So we see the AST once, we generate a closure, and then we run the closure in the loop, hopefully faster. And here closure is just function pointer plus data, a lambda in many languages. So let's try that out. This is slightly more complicated Rust code, but you can read type A as just being boxed in fun just says closure in Rust words. And this is essentially a function from v to an int. And now our function f takes an expression and produces a function from v to int, rather than taking an expression and the v and producing the result int. So it looks at the expression once and then uses the closure many times. The interesting operation here is the add. So add x of y, we first evaluate f of x to produce the closure related to x, then we evaluate f of y to produce the closure related to y, and then this box move vertical bar syntax is just say closure, and we run those closures by running those closures and adding the result together. Looking at the lozenges, we can see that the closure is about 1/3 faster than the AST. So this is a nice performance saving for code that is a little bit more complicated, but fundamentally doing the same job. If we want to move further and get even faster, which we of course would, we need to think about where the intermediate values go. With the AST and the closure, we're reusing the native Rust C stack in the operating system. So when we call f of x plus f of y, f of x will be put in a register, there'll be a function call to f, there'll be a return from f, and that's how it will evaluate things. Essentially, all the intermediates are stored by the native language. If we want to do better, we need to start taking care of those intermediates ourselves. And there are two broad strategies you can use. You can use a stack, or you can use registers. With a stack, the idea is you have a block of memory that grows upwards, and you're always talking about the top few pieces of data. So for example, our add will take the two elements off the top, add them together, and put a new element on the top, which is their sum. And we'll be doing a lot of operations like push and pop to make our stack the way we like it. In contrast, registers are a bank of memory that are accessed by index. So we'll see operations like R9 equals 1 and R7 equals R2 plus R9. So here, our add operation is not just saying add and implicitly take the information on the top of the stack. We have to also say which pieces of memory we want to add together. So let's try that. We'll try first with stacks because they're easier to compile to. And for something like I equals I minus 1, we'd end up with the code push minus 1 onto the stack, get the value of I onto the top of the stack, add, and then take the value of I from the top of the stack and put it wherever I is. And in this case, for maximum performance, we're going to put the values I and X at the bottom of the stack, so they're just indices into the stack. But if we look at the performance, it's actually a bit worse than closure. So let's see what the code to do this looks like. And I put a fragment at the bottom of the slide. So we loop. The first thing we do is we match on the tape.next, see what the code is. And then for the code push, we do stack.push tape.next. So we grab the -1 off the tape and push it onto the top of the stack. For add, we don't do any tape operations. We just stack.push the result of stack.pop plus stack.pop. At the end of this, we loop round to the top and continue again with the next operation. So in order to figure out why it's a bit slow, let's think of what happens on each operation. So after we've done our add, say, we'll be in the body state. We'll then jump to the top of the loop. We'll look up match tape.next, and assuming that there are many opcodes or many branches in our match, it will have been turned into a jump statement, where each alternative has an assembly code address associated with it. So we'll look at making a lookup in the match array of where we should go next, and then we'll jump there. So each operation has a jump, an indirect lookup, and a jump before we do the body. That's quite expensive. So what would be optimal? Well, we can't generate new assembly code on the fly. So we can't take our code for add and concatenate it with the code for push, because that would require generating new code on the fly. And that's our definition of cheap interpreter. It doesn't generate new code on the fly. So we must have a finite number of parameterizable chunks of assembly code. Therefore, we must jump between them. But we only really need to do one jump. And this use of only one jump to get between operations is known as direct threading. Let's look at how we'd implement that in C++ using extensions that are available in both GCC and Clang called computed Goto. We define our operations like push and add. And for example, for push, it's stack.push of tape.next, very similar. But instead of then going round to the next iteration of the loop, we immediately go to tape.next. And if we look at our tape at the top, we can see that it has the constants in, like 1 and 8, but it also has assembly code addresses. This && push is the computed Goto notation for put the assembly code address of push in here. So there's no loop, and at the end of an operation, we immediately jump straight to the next operation. So in the tape we've got above, we do the push and then immediately jump to add. So that's in C++. How do we flip this into Rust? Well, unfortunately Rust doesn't have Goto or computed Goto, so we have to fake it. Looking at the assembly code, we can see that tail calls are compiled into jumps, so we can just use tail calls. However, that's a little bit overgeneralization. On x86-64, with -0, tail calls are compiled into jump. And I suspect this is true of most architectures, but it's definitely not true in debug, where Rust deliberately and somewhat sensibly tries not to change the call stack. So it's not guaranteed, but at the same time it is compositional. Whereas with computed Gotos, we had to arrange for all our operations to be in the same single function. With Gotos via tail calls, we can put our functions in different files and link them up later. So here's an example of what our add operation might look like. It needs the stack and the tape, so it needs to take those as arguments. It does the stack.push of stack.pop plus stack.pop as normal. It gets the next value off the tape, and then it calls k open bracket normal function call, passing on the stack and the tape. And this will be compiled into a tail call with optimization. If we look at how the performance is, we can see that this stack tail call computed Goto approach gives us performance that is about a third better than Clojure. So this is worth having. This is a good improvement. Can we go any further? Well, yes, we can switch to registers. And if you look at the lozenges, we can see that the register approach is almost as fast as the native Rust. So let's think of what the trade-off is here. With the stack, if we want to do x plus 1, we'd typically push on x, push on 1, and then do an add. Whereas with registers, we'd set maybe register R2 to 1, and then do R3 equals R plus 1. The stack has done 3 instructions, whereas the registers have only done 2 instructions. But the stack's instructions are more compact. Our add doesn't have to specify the registers, so it's only 5 words if we use a reasonable encoding, whereas the registers would be 7 words. However, the R2 equals 1 can certainly be done outside the loop, so now the registers can be a single instruction that is even smaller than the stack instructions. So fewer instructions, longer instructions, more opportunity for optimization and emitting less instructions, and that brings us down to much closer to the performance of the Rust. So what can we do to get even faster? Nothing. We could try using a compact tape, so representing registers as 1 byte rather than a word, and that results in a few percent slowdown. We could try using a better register allocator, so there were less registers, and thus they were more cache friendly, but on this particular benchmark it doesn't make any real difference. In a much bigger expression with more intermediates, it probably would. What are the things that would work, but we consider outside the scope of this talk? Well, we could transform the code. If we see 2 plus 4, we don't have to evaluate that every time round the loop. We could just replace it with 6. Similarly, we could use bigger fragments. So we have a lot of addition. Maybe we could introduce a code that was add 3 things together instead of just 2 at a time. That would certainly reduce interpreter overhead. And then finally, we could generate fresh assembly code at runtime, but that is no longer a cheap interpreter. So let's look at the techniques we've gone through. Of these, AST is 6.4 times penalty, but the lowest effort and the cleanest code. So this is definitely where to start from, and it might often be the case that the interpretation overhead is not a significant portion of the evaluation, so it's worth sticking to. If you're looking to do better, a Clojure-based approach gives a 4.8 times penalty. So it's a little bit more effort, but not much more, for a nice improvement in speed. Finally, if you're looking for the best performance we can get in a fairly cheap way, we can go for a register-based approach with a 1.4 times penalty. But this requires much more effort. For example, it requires a register allocator, and you'd better be using unsafe operations to do the register indexing. We tried these approaches on the Starlark language and saw improvements which were approximately half of what you'd expect given the penalty, suggesting that originally interpretation was about half and evaluation of operations was about half. So it's a worthwhile technique that can give meaningful improvements without going to the full cost of generating assembly at runtime. Thank you very much.
Thank you, Neil. So this is really a cool description of what of the effort you guys are putting to make the developers' life easier. I was wondering, out of those 3 options in production now, which one did you go for? The one that was easiest to implement, or the one that was the most performant?
In fact, the middle one, the Clojure-based approach, because it really isn't much additional effort, but it gives you a good win. We will probably move to the register-based approach in due course. It's almost certainly worth it.
Yeah. And do you see other applications for this work beyond just improving the more exotic implementations of languages?
So I think there's very much a long tail of languages. So I think there are a lot of these kind of exotic languages that are defined one-off for configuration. So I think the techniques could very well be reusable to a large class of them. People have spent a lot of time thinking, how do we wring 0.5% more improvement out of V8? But they haven't really thought so much about what does it look like to write something that's called thousands of times a day or hundreds of times a day rather than billions.
Yeah. Okay, let me just check if we have any fresh questions on Twitter. All right. I think that was all for now. Thank you so much, Neil. See you later in the panel.